Okay, so this is lecture 20. I'm going to continue talking about the terminology for discrete time Markov chains. In this lecture, we're going to talk about what the period of a state is. So remember from previously, when we have a discrete time Markov chain, we typically represent that with the transition diagram. So here's one Markov chain in which we have 4 different states, and we have equal probability of going to the right or to the left. So we have equal probability of going from 1 to 2 or 1 to 4. Okay, so what we're interested in this lecture is what does it mean for a period of state 1 to have period, let's say 2 or 3, or whatever it happens to be. So let me give you the definition of period. So for each state I, the period of the state is denoted by d of I. And it's the greatest common divisor of all the values of n, so that remember what this means. The probability of going from state I to state I in n steps is positive, and n is greater than or equal to 1. So this is a little bit hard to kind of grasp what in the world are we talking about and how do we find our period. So the intuitive idea is if you're starting in state I, is there a positive probability of returning to state I in a finite number of transitions? So if I start in state I, is there first of all a way of getting back to it? And then if there's a way of getting back to it, then how many times does it take me to go around to go through different states in order to get back to my state I? And once I have all those values, how many transitions it takes, all those values of n, then I find the greatest common divisor of all of those. And that's what's called the period. So if you have a period that's greater than 1, then the state is said to be periodic. If it's equal to 1, it's said to be aperiodic. And you can also have that d of I equals 0, and this basically means that once starting in state I, it never can return to state I again. Okay, so let's go to an example because it's going to make a lot more sense when we actually talk through some of the examples. Okay, so here we have state 1. So let's first of all, before we actually do anything with this, let's give some of our terminology that we've been talking about recently. So here, all of our states communicate with each other. So that means that they all are in the same communication class, which means it's irreducible. So now let's look at 1 here. The probability of starting in state 1 and going back to state 1 in n steps, the probability that this thing is positive is true when n is 2, 4, or 6. So let's look at the diagram and see what this means. Okay, so here if I'm in state 1, then how long does it take me to get back to state 1? Well, I could go to state 2 and then I could come back to state 1. So that would be an n of 2. I go, come back, this n's 1, n's 2. So I have n equals 2. I could go state 2, state 3, state 4, and back to state 1. So that's n equals 4. Or I could have gone 1 to 2, 2 to 3, 3 to 2, 2 to 1. So there's lots of different ways that I can come back. So if I keep doing this, then all of them are going to be multiples of 2 here. So 2, 4, 6. So the greatest common divisor of all of those is 2, which means the period of state 1 is also 2. So we really don't want to have to do this with all of the states in our Markov chain. So we have this nice idea that the period is a class property. So if two states are in the same communication class, then their periods have to be the exact same. So going back to example 1, what that means is we don't have to walk through this example for 2, 3, and 4. We already know that all of their periods are also 2 because they are in the same communication class as 1. Okay, so here's another example. So if we look at this, we have state 1 can go to state 2, state 2 can go to state 3, and state 3 returns to itself. So what do we know about this system? We know that it has 3 different communication classes. None of them communicate with each other, so they're all in their own individual communication class. I can go from 1 to 2, but I can't go from 2 to 1. So also some of the other terminology that we've looked at. So if I'm in 1, if I'm in this communication class, I can get to something outside of it. If I'm in 2, I can get to something outside of it. But if I'm in 3, the only thing I can do is come back to 3. So 3 is closed, 1 and 2 are not. Okay, so the other thing is if we're looking at, now for this one we have to figure out the period of each of our states because they're all in their separate communication class. So the period of 1, well, once I leave 1, I never come back. So that means the period is 0. The same thing's true for 2. If I'm in 2 and I leave it, I can never get back to 2. For 3, notice here, with 3 it comes back immediately. So the period of 3 is 1, because I can return to state 3 in 1, 2, 3, etc. transitions, which means that state 3 is what's called aperiodic. Okay, so here's another example. If I look at all this from any state, I can get to every other state in here. So that means it's irreducible and it has one and only one communication class. So if I just look at one of these states, then I can figure out what happens with all my other states. So if I look at 1 here, how many steps does it take to get back to 1? Remember, I'm looking at all the possible ends. So I could do it in 1, 2, 3, 4 transitions. I could do it in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that was 4 and 10. But also remember I can do it in 1, 2, 3, 4, 5, 6, 7, 8. 8 transitions. So here, n equals 4, 8, 10, 12, etc., etc. Greatest common divisor of all of these is 2. So the period of every single state in our system, in our Markov chain, is 2. So here's another example. We've seen this one before, right? So we have 5 different states. We have 1 and 2 communicate, 3, 4, and 5 communicate. So we have 2 communication classes. We've talked about this before. Both of these are closed, and it is reducible. Okay, so if we find what the transitions for one or 2, then it's the same for the other one. And same thing, if we find out one of these, then it's the same for the other. Okay, so notice here, if I'm in 1, I could get back to 1 in just one time step. So n equals 1, which automatically means that the greatest common divisor has to be 1. So it's aperiodic. Whenever I have one of these states where it can come back to itself, such as here with 4, it can always come back in n equals 1 step. So that also means that your period is 1. So whenever you see it coming back to itself, the period is always going to be 1. And so it's going to be aperiodic. Okay, so that's the end of talking about the period of the state. Next time we're going to give some more terminology of what it means to have a recurrent versus a transient class.